Hi, I'm here to talk about the covariance step in nlmixr, what changed and why. Three things changed in the covariance step for this release. The default covariance step now covers every parameter, two new covariance methods, SA and IMP, that can be used almost anywhere, a genuine new covariance method that Hidi created, an exact analytic covariance. Let's start with the new full covariance. Now the additive residual error standard deviation is calculated for all methods. Before 7.0, the standard error was missing. We've always leaned toward using the inverse Wishart distribution for simulating uncertainty in omega and sigma. When implementing nlmixr, we thought by not having these standard errors, others would simulate with uncertainty with the inverse Wishart distribution too. Additionally, getting real standard errors for those terms took real additional work. Now this new work really doesn't change how we think about simulating with uncertainty. However, these values inform how well these parameters are estimated and are frequently requested and useful in other methods. If you look at the full covariance matrix, you'll also see the omega block standard errors. The covariance matrix is named so you will never guessing at which covariance term belongs to which estimated omega element. So what's still skipped? Fixed parameters, inner occasion variability parameters, and mixture probability parameters. Everything else is in the covariance matrix by default. The second change is bigger than it sounds. Two covariance methods stopped being tied to one specific estimation method. The new SA and IMP covariance methods can be requested for practically any fit and also be computed post-fit. This post-fit covariance step occurs at the converged estimates of the mixed effects model. setcov calculates the new covariance and folds it right into the fit. Once it's calculated, it's cached so you can flip between covariance methods on the same fit without paying the calculation cost twice. Here's the full list of supported covariance matrix methods. Some are still only found in their corresponding methods. If you specify an empty string, the covariance step is simply skipped. This lists the default covariance methods. Most defaults stayed put because they were already the right choice for that family. The last piece is cov method equals analytic itself, and this one is based on Hidi's work. For the new analytic method, the population objective is a data term plus a log determinant penalty term. The gradient only needs second-order sensitivities. For more details, you can read the corresponding paper. The analytic gradient has no step size and no finite difference noise, so it is not erratic or biased. It is exact. It is only limited by the accuracy of the ODE systems themselves. On a warfarin case study, one compartment, oral absorption, 10 subjects, a correlated random effect block on clearance and volume, and a diagonal random effect on the absorption rate, the analytic standard error matched an independent non-mem run to every figure they reported. The finite difference standard error only tracked that value over a narrow middle band of step sizes, too large a step and it's biased, too small and it gets erratic. The analytic value just sits there, flat, no step size involved at all. To summarize, the default covariance step now covers every estimated parameter, SA, IMP, analytic, and the finite difference methods. You can switch after the fact with setcov. The analytic covariance gives you an exact standard error. Thank you, and thank you to Hidi and the rest of the Leiden team for the analytic covariance work behind this release.